This is 5.1 systems of linear equations in two variables. So here we have a system of equations, and it's basically we have a linear equation right here and then here, and what we want to do is find it, solve it, and there's different ways we did this. Now you actually did this back in Algebra 1 and Algebra 2. It's just go through it kind of quickly just to refresh your memory. So one way to solve this is the graphing method. So what we could do is just graph, this is a line, the first one's a line, the second one's a line, we could graph them, and then find the answer, which is the point of intersection, like where do they cross at? And that's what we're going to do here. So let's look at the first line. So if we have, and most of us solve for y equals mx plus b, so if we take 4x plus 2y equals 6, and then we're going to solve for y equals mx plus b, and we're going to get this. And then if we graph that, again, that's your y-intercept, and it'll go down 2 over 1, down 2 over 1, down 2 over 1, down 2 over 1, or up 2 and 1 to the left. All right, and then that would be the blue line that we would graph and connect the dots. We'll do that in a minute. And then the red, if we solve for y equals, we take this one and solve for y equals mx plus b, you're going to get y equals 2x minus 1. So we're going to start at -1 and go up 2 over 1, up 2 over 1, up 2 over 1, up 2 over 1, down 2 1 to the left, down 2 1 left. So notice when I do connect these dots, the point of intersection that you see crossing there happens to be the point 1, 1. And just to double check, I mean, if I wanted to double check this, if I put 1 right here and put 1 right there, does it equal 6? Yes. If I put 1 right here, put 1 right there, does it equal -1? Yes, it does. So that is my solution. Now, that's how to solve it using the graphing method. Now, let's solve it using the substitution method. Well, the substitution method, what I would notice is this y right here is all by itself. So it's easy to solve for this one. So I'm going to take y equals 2x minus 1. And then I'm going to substitute that in. That's why it's called the substitution method. I'm going to substitute it in to the other equation for the y. So the blue equation now looks like 4x plus 2y equals 6. And I'm substituting in 2x minus 1. So instead of writing the y, you're going to literally replace it with what the y equals, 2x minus 1. And then you're going to solve this. So we have x is 1. And then when we substitute 1 back in, we're going to get 1. So we solved it by the graphing method. We solved it by the substitution method. Now let's look at the third method. It's called the elimination method. Well, notice that both of these equations are in standard form. In other words, in columns, you have the x's lining up in a column, the y's lining up in a column, and the numbers lining up in a column. And if I added these right now, like straight down in a column, nothing eliminates, but I can do something to it. Well, notice this first equation. If I multiply it by something, or in this case, divide, I'm going to divide everything. Everything has a 2 in common. So I'm going to divide everything by 2. And that first equation becomes 2x plus y equals 3. I just divided the first equation by 2. Or sometimes you got to multiply it by 5 or something like that. But here, notice here I have the original problem, the original equation. And now if I added these columns in a row, so I added the x columns, they literally eliminate. And then add the y column, I have 2y. And then add the numbers column, I have 2. And then divide by 2, so y equals 1. And then substitute y back in to one of the original problems, and you're going to end up getting x equals 1 as well. So we solved it 3 different ways: the graphing method, the elimination method, and the substitution method. All right, and then there's a possibility when you start graphing these lines, what we just now got done doing is we did this problem. They cross at one spot. You graph the red line, you graph the black line, they cross at one solution. And you'll also notice anytime they have different slopes, when you set it into y equals mx plus b, if they have different slopes, then I know they're going to cross at one solution. There's also another scenario like this one right here. If the lines happen to be not crossing at all, then there's no solution. They're parallel. Parallel lines have the same slope. So if you actually do solve for y equals mx plus b on both of them, like solve both equations for y equals mx plus b, and if you notice that the slopes are the same, then you notice, without even graphing, you notice that they're parallel, which means there's no solution. And then the third possibility is, what if I graph the black line and the red line and they literally lie on top of each other? So in other words, they're the same equation. Well, that means every single point is going to be in common, so there's an infinite amount of solutions. All right, so let's look at a possibility, and this is without graphing. So here's two examples. So I wrote it in, I already have this worked out for you, but notice in black is the original problem, and if I multiply the top equation by -2, and then I added these. Well, if I added these using the elimination method, notice I get 0 equals -4, which is not true. Notice the x's cross out and the y's cross out, so you end up getting 0 on that side of the equation, and so there's going to be no solution. Which, again, if you did take this equation and you took this equation and solve for y equals mx plus b, that just means they're parallel. All right. So whenever there's no solution, that means they're parallel. Again, you don't have to solve for y equals mx plus b. You don't have to graph it. You can just purely use the elimination method as long as you know what this means. What 0 equals, when you end up getting a false statement, then there's no solution. So let's look at another example. So here I have written in black, and I have two equations, and I multiplied solving by the elimination method, and notice I end up getting a true statement. 0 does equal 0, and because when you subtract these are all going to cross out, and so you're going to get all solutions. So, and plus you can notice anytime you get all solutions, that means they're the same equation, which you can obviously see that they're the same equation. You better do that. So again, you can solve by elimination, substitution, or graphing, but this is a quick way to tell as well if the x's and y's both cross out and you end up with a false statement, it's no solution. If you end up with a true statement, it's all solutions. All right, so let's look at a live application of this. So George rows a boat upstream for 4 miles in 1.5 hours. And then coming back downstream, obviously, if you've ever rowed in a boat going upstream compared to downstream, or even swimming upstream and downstream, you notice there's a current that you're swimming against, or you're swimming with the current, and it makes all the difference in the world. So coming back downstream, it only takes 45 minutes. So two questions: how fast is George rowing, and then how fast is the current? Well, notice what I have written in red. First, you have to notice certain things, and I'm going to assign them different variables. So x is the rowing speed, so that's what I have first. I just designated x as the rowing speed, however fast George is rowing. And then, of course, I designated y as the current speed, the current of the river. And then notice downstream is x plus y, because if you're going downstream, you're working with the current. So that's why it's x plus y. And if you're going swimming or rowing upstream, you're going against the current, which is harder. So it's going to be x minus y. And then I also want you to notice that, two other things. One, the distance formula, d equals rt. And I also want you to notice that George rows from one place to another place and then back down. So the distances are equal to one another. So that's something very important to notice here. So we're going to go ahead and set up some equations and then solve it from there. So George first started rowing upstream. And notice the formula is r times t. So the rate that he was going upstream is x minus y. That was the rate. That's what we figured here, the rate of going upstream. And then we're going to multiply it by the time, which again, going upstream took 1.5 hours. So we're going to do 1.5, or as a fraction, 3/2. So that's the well, and we know the distance is 4 miles. Okay, so notice going upstream, this is the first part of his trip. That's what we noticed. And then similarly, going downstream, so we know, notice going down, it's the same distance, 4 miles, and then we have x plus y, and it only took him 45 minutes, or 3/4 of an hour. So notice we have two equations here and there. And what we're going to do is solve those two equations using, you can use substitution or elimination or graphing, but elimination is going to work out very nice. So I'm just going to literally rewrite it, and then we're going to solve from there. Okay, so what I did is I basically just used the distributive property, and then I lined them up because I want to use the elimination method. So I lined up the numbers, the x's, the y's. Now, it may look ugly right now, but what we're going to do is just get rid of those fractions. We're going to multiply everything here by 2, and we're going to multiply everything here by 4. So that way it's going to cross things out here. So the blue equation now becomes 8 equals 3x minus 3y. The green equation becomes 16. All right, so now if we use the elimination method, we solve this. Notice we're just going to add the columns. So we're going to get 24 equals 6x. Notice the y's cross out, they eliminate, and so x equals 4. So notice what we just saw, we just now found the rowing speed. X is 4. So George rows, how fast is George rowing? That's the first question. George is rowing at 4 miles an hour. So then how fast is the current? Well, what we need to do now is substitute that back in, and we're going to substitute it back into one of the, normally you plug it into the original problem, but remember this and this is the original problem, just we got rid of the fractions. So I'm just going to plug it back into whether the blue equation or the green. I'm just going to plug it back into the green, the blue. So we have 8 equals 12, because I did 4 plugging in right there, and then minus 3y. So notice the current of the river is 1 1/3 miles an hour. So that's the current that they're doing. And we use a system of equations to figure that out.